Yeah, here's the best one.
We have not. Yeah, it's quite hard in terms of simulations, I think. Yeah, because of the like way we created a transfer, is required to add, and it's kind of necessary actually, unfortunately. Yeah. So I'm thinking of switching over to like smart,
You have ideas about that?
Yes.
So my idea was that will take a little while to stand up.
It'll take a while in terms of
But
like
start. So I'm Eisenstein, and I'll be leading the discussion today, although really I hope that's mostly you guys leading the discussion because I didn't prepare more than maybe about 10 minutes of things to say, which I think is the spirit of this. We're not really supposed to show slides, but to come here and not show some pictures would be ridiculous. So if you haven't seen it, the QR code is actually on the page here, but this is our public website. for browsing the images, and it's really, it's been a wonderful site for us. We actually use it as our primary method for doing quality assurance on the images and just lots and lots of things. So this is the public version, but you can just pan around out to the full survey, zoom in, zoom around. It all goes down to 30 millisecond pixels, so ridiculous resolution. If you come up here, you can get all the various bands that are in the survey. So you can click between, click between. Let me put the source over here. Click between looking at 0.9 microns, 1.5 microns, 2.7 microns, 3.5 microns, 4.4 microns. You can do various RGB images, combinations of things. You can get to the HST data. When you're tired of looking at individual things, you can then come and actually click open all the SEDs and actually click and pop up plots of everything that's being shown with the photometric redshifts. And we have our spectral link on here too, although we don't yet have very many spectral. So it's just a really fun way to actually browse the sky. There's also a version that's optimized for the public that has sort of simpler captions and fewer options. And when we had the Cambridge Discovers the Universe Festival a month ago, we had a couple Chromebooks and 5-year-olds were just sitting here panning around on the sky. It really works very, very nicely. So this is data from the JADES collaboration, which is something I'm a part of. This is an effort between the near-infrared camera team and the near-infrared spectrograph team to use about 800 hours of guaranteed time in the first year of the mission to do deep field pointings of the good south and good north fields. These are the famous Hubble ultra deep field, Hubble deep field region. But the data comparison between HST and JWST is honestly not much of a comparison. It's so amazing how much better we do when you can actually look properly into the infrared. So, of course, this is really what the telescope was primarily designed to do. If you go back to the earliest days, it's dubbed the first light machine, and it's because the goal was to study high-redshift galaxies in the infrared. Of course, it does many, many other things, and perhaps people want to bring those up to date as well. So, of course, now the mission's been much more generalized in its scope, but it really does work as advertised to be able to investigate early galaxies. Of course, the big reason here is that the sky is really dark between about 2 and 5 microns. So if you're in the optical, you're getting a lot of backscattered light from the sun off of little dust in the solar system. And when you're off beyond 5 microns, that same dust is absorbing sunlight and glowing with a black body peak around 10 or 20 microns. And so there's a dark window between 2 and 5 microns that is basically held to from the ground, but really dark in space if you can cool your telescope. And this is exactly where all of the rest optical and rest ultraviolet light shifts off to when you're trying to study galaxies beyond redshift 3. And I think another major aspect of JWST is that the instruments are extremely capable. It's not something where there's like, oh, you have one camera and it has fixed filters, and if you don't like those fixed filters, wait for your next telescope. It's a very, very powerful camera with a lot of different filters. And the spectrographs on board are extremely powerful. This is the first time we've had a configurable slit mask in space. So, you go to a telescope, you want to get multiplex of 100, that means you have to sit there and insert a piece of metal with carefully drilled slits in it. You do not have an astronaut sitting next to JWST with a laser machine. Instead, you have a tool that has 250,000 little magnetically configurable micro shutters that allow you to build a configurable slit in space. So you can get multiplex of order 150 at a time. And of course, it just goes super, super deep. So the faintest dots you see in this image, which you probably can even see by eye from without going up to my screen, are about 30th magnitude. So that these are really, really faint objects. Okay, so when we think about studying galaxies up beyond redshift 6 or 10, we're primarily looking for things that are Lyman drop candidates. And I think a big impression that I have from the early returns from the mission is that it's not a single story. If you thought that like you sort of got too enamored of the star forming main sequence, red sequence, blue cloud, star forming main sequence kind of narrative, I think that's not even all that great a narrative at redshift 1 to 2, but it just is clearly not the full story. So you just have to really wean yourself from the idea that all the galaxies at high redshift are doing the same thing, following the same narrative. We see examples of galaxies that are bursting. We see examples of galaxies that are having a break, not forming stars very much. We see objects that are very compact. We also see objects that are more extended, and we're starting to really tease apart substantial sort of overdensities and protoclusters. So one of the real, I think, very nice results in these early days is how the spectroscopy is actually revealing redshift clustering. So we have one example of redshift 5 that has, I think, 100 members, spectroscopically confirmed. It's really, there's a lot of richness in the data. I think last week Jake talked about AGN, and there's plenty of AGN signatures in these galaxies, and a lot more than 1 out of 1,000 or 1 out of 100 galaxies showing AGN activity of some form. There's also been, I think, interesting results as regards chemical abundance patterns. No surprise, high redshift galaxies are low metallicity, but it's also the case that the abundance ratios of some of those elements are starting to be shown to be not the usual things. So there's a lot of really wonderful things to do here. Yeah.
How do you separate out what is AGN and what is galaxy?
Yeah. Not easy. So when you look at, I think this is a long-standing problem for any deep field thing. When you look at a bright galaxy at high redshift, you should be at least imagining that probably AGN had something to do with the brightness. So of course, compactness is a first step. If the thing is not very compact, then the AGN is probably not very important, at least for the ultraviolet light that you're seeing. We do see examples of broad lines. So one of the things that's really nice in JWST is that the spectrographs have enough spectral resolution that you can really see the broad lines. And I'm here thinking primarily of H alpha and H beta, but also sometimes with oxygen 3 as well. So that when you see a sufficiently broad line, then that makes you think that probably an AGN is involved. But even there, you start to worry that there could be outflows that could be driving the velocities up. So there's even some mischief in terms of being certain in that world.
So you talked about compactness. These galaxies are spatially resolved, is it, in JWST images?
So a lot of them are. We also do see examples that are unresolved. So for us, unresolved is about 0.02 arc seconds.
0.02 arc seconds.
So very, very small. But of the 4 high redshift ones that we've published spectroscopically, 2 of them are unresolved at that level, and 2 of them are resolved. And then the example that's
unresolved, you just call it an AGN, dominated on?
Oh, not necessarily. So I don't think that would be the proof. No, I think galaxies may be, actually, these are really small galaxies, and they may be, resolved means that it came out at 0.03 or 0.04, like they're still really small. So no, I think, if you can see fat enough broad lines, then okay, good, that's very nice. But if you don't, then you would prefer to be looking for emission line ratios. So look for certain high excitation lines, and again, you're working a lot on that. So that's a good path. But we also see clearly that these high redshift galaxies don't have the same emission line behavior that low redshift galaxies do. They show much higher ionization structures. And so, for example, at low redshift, the oxygen 23727 line is a very common, strong line, and oxygen 35007 is often there, but it's not usually the dominant line in a pulsar galaxy. At high redshift, the O3 line is booming, just enormously strong, stronger than H alpha, and the O2 line is hard to find. So I think that just generally says you're looking at hard ionizing radiation. And whatever the stellar pops are, because they're low metallicity, are driving that. And it's clear, I'm sure you can tell us much more about this,
No,
So sometimes the AGM will show up with the helium-2 1640 line. So that's a pretty good, that one's pretty convincing. If you find that, great. If you fall short of that because it's a faint line, then you're looking at other indicators. And I think there's a paper coming out soon about trying to untangle these things, but it's not, I don't think it's crystal clear. These ambiguous answers. Things that if you saw them at low redshift, you would have put them in the AGM. But I think the general context has changed so much that the standard BPT type of diagnostics are not what you need. They're not good enough. You need others.
Because there's too much star formation and UV from stars, or what's the problem?
Because the UV radiation from the stars is too hard.
Too hard, okay. Oh, because of the metallicity.
Yeah, that's the
Oh,
metal.
wow, okay.
Did I do the arithmetic right that 102 arc seconds at redshift 10 is a kiloparsec? Is that about right? I'm just trying to get
No,
something.
it's 100 parsecs.
100%, okay. I did do that right. Okay.
There's also some versions of the BPT diagram that goes to the higher redshift, like quite empirically. But do you think that we can just like put all of your data just, on those diagrams and just, basically mark them with, in terms of the redshift, and then compare them with the theory and just try to see is there any trend that we can look for?
Yeah, I guess when I said BPT, I meant the sort of classical
Exactly.
oxygen line. That one I think is breaking down. But yes, indeed, you want other line ratios that are more sensitive to the harder emissions. And then it's, one can do this, and the challenge becomes quickly, those lines are not the stronger lines. Like they're just not as much flux. So, and these objects are 28th or 29th magnitude, so when the line is weak, you need a very long spectrum to go in.
So the follow-up question is that do you think it's time to invent new BPT, like, in terms of new, like, emission ratios?
People are definitely working on that, things like that. And again, 1640 is great when you have it. It's just that we don't see it in all cases. Cases that we otherwise think are AGM.
So this spectrum down at the bottom, that's the 1640 line that's labeled helium-2, is that right?
Okay. Yeah. Okay. So the spectrum here at the bottom is the spectrum of GNZ11. So let me just say the GNZ11 was the brightest high-redshift candidate known in these fields from HST. So this was not our. We didn't find this object. This was known before. It's 26.5 magnitude. So
Okay, so a lot right here.
And this is the spectrum that came out of JWST for it. So this is a lovely, lovely spectrum.
Yeah.
With lots of lines. Now I think that the claim is that is not the 1640 line. I think it's actually the oxygen 3 line that's
Right
closely
beside it.
blended. And when we also have prism data on this object and grading data on this object. This is the prism spectrum, the higher resolution grading data that I think shows that this is not the helium line in this case. However, we actually do think that this object, well, the team has some disagreements. I think the majority of the team thinks that this is actually an AGM candidate. Not that the entire thing is an AGM, because it is also slightly extended, but there's
If the ionization structure is different, and the lines that might be excited are different, is there a challenge in even identifying the lines if they're so broad in the first place, or is that just
this breadth is because of the resolution of the spectrum. So these lines are narrow.
yes?
If you-
Okay, so the width that I'm
this
seeing
is a resolution 100 spectrum. So what you're seeing,
Okay.
the 1000 spectrum does not print well on these.
Yeah. Okay. Interesting.
But no,
Okay.
this system does not have particularly broad lines.
Okay.
Think, I can't remember exactly, but 300 or 500 kilometers a second, something
Okay.
very normal.
Interesting.
Yeah.
Thanks.
Yeah. Okay, so just turning to the back, an obvious topic that I thought people might want to be talking about is the thing that's been on all the press articles for the past 15 months, namely, are there too many high mass or high luminosity galaxies redshift greater than 12? So the plot at the top on the left here from Heinlein is a catalog of candidates that came out of our survey, and the gray points are all the previously known ones, and the orange ones are all the new ones. So going deeper makes a huge difference. And there are some objects on this plot that go out to a redshift of 14 or 16. But we also are careful in our paper to plot all these SEDs. And I think you will, if you go to inspect those SEDs, you will find that these are not gold-plated candidates. I mean, we wanted to be complete in what we published. When you look at redshift 8 or 10, there's lots of gold-plated candidates. There's, I mean, just really, really nice classic dropout SEDs. When you get out to redshift 14, 15, 16, the samples get ratty. It's not necessarily not always lack of flux, but you don't have as many filters left. And I think there's a fair bit of evidence that the universe has some population of other strong dropping Balmer jump or 4,000 angstrom break galaxies that serve as kind of a floor of false positives on some of these things.
Is there a feature at redshift 10? Like,
In the photoz's, yes, and that's because how do you get these photos? You get them by watching for this. You're looking for an SED that's a big blue continuum and a drop.
okay.
But then you have certain filters.
Uh-huh.
And when the drop is happening,
Yeah,
at certain
okay.
places, the filters are not very good at distinguishing small changes in the
Sure.
drop.
Okay.
And so you get sort of, the modes of all those distributions will kind of shift around. So
Sure.
this is not,
Yeah,
this is
yeah.
almost certainly a methodological systematic of the photoz's. And we see that in the simulations of it. When you simulate the colors through these features.
Yeah. Yeah.
So in particular, redshift 10 is where the Lyman output line shifts from the F115 filter to the F150 filter.
Okay.
When the line is between the filters, that's where you get rather poor photosy.
Yeah, okay. So it's almost like whatever error bar I would imagine shifts as a function of where you are relative to those bands kind of thing.
And also that the answers are not, the photosy answers are not unbiased,
Correct.
but in a way that varies with redshift.
Okay.
And that causes a bunch of.
Interesting. Thanks.
So, we certainly should have some conversation about the, the implications of the high redshift luminosity functions and so forth. But I just would caution that, I don't yet believe that there's an excess of these objects, and it's because I'm very nervous about false positives. And we've already had examples of false positives where people, thought there was a galaxy at redshift 16, they took a spectrum of it was a redshift 5, and it was not a gold-plated candidate going in, but it didn't leave as a gold-plated candidate. But then even once you're done sort of weeding out your false positives, there's lots of other reasons why it's really hard to turn ultraviolet light into something that's a challenge to cosmology, because you have to decide what the light is coming from. If you start saying the word AGN too many times, you can start to explain high luminosities in any given object. But of course, then there's also major uncertainties in how to convert UV light to mass. When you're at more modest redshift, JWST is a real boon for this because you're finally able to probe into the rest optical part of the SED, where you can see the more intermediate age stars, and you can see the strength of the Balmer jump with the 4,000 angstrom break. But when you're out beyond redshift of 10, all you have is the rest UV. That's just not able to constrain how many old stars or older stars are in the system. So the masses are really uncertain. And that's before you get to like actual theory problems, like what is the contribution of binary stars to ultraviolet stellar populations or things like that. There's also a fair possibility of mischief in priors when you do SED modeling, so what your prior is, how you regularize the star formation histories, that can affect masses a lot. And then also how you propagate photosy uncertainties. If all your photosies are uncertain and the mass and the luminosity function is crashing down, then you have sort of an Eddington bias that you'll always, it's not quite Eddington, but you'll give a systemic bias that there's a lot more lower redshift things that want to scatter into your sample than there are higher redshift things that want to scatter into your bin. So you will systematically overestimate the photosys just by that prior volume type of thing. So
You were mentioning at one point like simulating to reconstruct, like you were talking about these filter features, but like, do you think that's part of the path forward? Is like making
So you always want to start with synthetics, just to make sure that you understand your detection limits and your probability uncertainties. But that's not, I mean, lots of teams are doing that in various ways. So I'm not trying to throw people under the bus for that. People are trying to do that sort of stuff. No, I mean, I think you want deeper data and you want spectra to actually try to confirm.
I don't know if you can tell us more about the timescale of the survey. I mean, I'm thinking about alternative uses, but so you have, I'm always doing that. So, I mean, you've got a bunch of imaging data and a bunch of spectroscopies over what kind of time period were these?
18 months.
18 months.
It should have been all done in 12 months, but the scheduling, the timescale didn't permit that. So we're just basically finishing up our second season.
And for any given chunk, what is the sort of typical repeat time?
Okay, so JWST is a pretty brutally bad telescope for time domain astronomy because it just takes forever to slew anywhere. So your goal in JWST usually is you go to that spot on the sky once, you take all the data you'll ever need. you try not to have to come back. But in practice, we did have to come back because I couldn't schedule all the time in one go. So we have a lot of data that's separated by 1 year, which is quite interesting because that does mean you get supernovae in that 1 year. And we have other little bits of data that's sort of separated by a month.
What's the sort of overall area, solid angle of
The full solid angle will be about 200 square arc minutes, but that's not, we don't have that all in hand yet. That's just our program. There's lots of, I mean, there's many other programs. I don't want to sort of totally make this about J's. Like, so there are programs that are doing sort of, I would say, medium depth data over, again, scales of 50 to 100 square arc minutes. There's one program that's taking rather shallow data by JWST standards. However, I think it's half a square degree, so that's big. And then there's other programs that are trying to do very deep data, in single pointings, either in blind field pointings or around lensing clusters. So there's a bunch of work that looks at tries to use gravitational boost from the magnification of a cluster. Very reasonable thing. So there's some really lovely work in those fields as well.
Even when you're there for the single pointing, you get exposures on the time scale of hours or a day?
Oh
Or
yeah, if you want time scale of hours, yeah, that we have. We got lots of
very
that.
fine pixels, so you might see through
It
the
would be easy to see.
yeah.
Sorry.
I'm just saying, I was answering the question he didn't ask, which is that you, on that timescale, you could easily see solar system objects.
Oh
You
yeah,
would,
yeah, trivially.
on that.
We don't actually see them because we're a high latitude, but there's also been a program that was doing that looked at low ecliptic latitude.
Yeah.
So we beautiful aim for the extra background. Yeah. It's ours is easy. So on the one hand, I'd be all set to stand up here and say, well, there's too many of these high redshift candidates are not going to pan out, and it's just early days to be too concerned about breaking the universe. But I think an example of results that I found not of that form are that one of the I think really interesting things about JWST is the spectral resolution and spatial resolution is high enough that you can actually do dynamical mass measurements on some of these galaxies. So people have actually measured rotation curves of redshift 5 galaxies and measured either with the slit spectrograph or with the slitless prism. So I have a couple papers there listing that. And so, those often come up with rather large velocities, which means that there's just RB squared over G is actually a lot of mass. And you get masses that are dynamical masses that are considerably larger than the stellar masses.
Those are absorption lines,
Those are emission lines.
emission lines, so you could play with it.
Absolutely. So yeah, you always want to be have to try to figure out how to validate these things. But so I think that's early days. I mean, that's really that's the level of the handful
But it
of
follows
objects.
the normal rotation.
It does look pretty normal.
Yeah.
But then, that would be, to me, is like you got to get to masses somehow. And if you're nervous about the stellar SED mass modeling for lots of good reasons, you really would like to get to dynamical masses. But I think there's routes to do that. So that's really exciting.
What kind of physical scale are these dynamical mass measurements on? Like, are they looking at the central?
Yeah, no, really small. So like 0.3 arc second. where you have the light,
Yeah.
right? So that's I think a fair point. Like usually when you're talking about like, does this break the universe? You are, you know, it's a very tortured, you know, more tortured than the distance ladder, right? You have to, you're gonna start with some light. You're gonna try to model that in terms of stellar population, try to get to a mass, but that's just the stellar mass. You then have to guess about the gas mass. And what you really want is the halo mass, which is on a larger scale. So that's always gonna be tricky. So I think one of the things I'm kind of interested in is the fact that we do see these multiplets and sort of proto-groups. If you can actually get to dynamical masses of those sets, which is not impossible to think about doing. You know, if you had an object with 10 redshift measurements on the scale of 10 arc seconds, then that probably is measuring something about mass. Now, any one of those would not, just like cluster low redshift being a really difficult game to play for cosmology. I'm sure that will also be true at high redshifts, and you'll need to have a bunch of examples, but it's, I think it's in play.
Are there any like measurements at kind of intermediate redshift of dynamical masses versus stellar masses and how they somewhat relate depending on exactly what scale you're looking at? Because like the dynamical masses, you can imagine if you've got a very dense core of a galaxy that is the bright thing that you can then see, that would kind of lend itself to you getting a high dynamical mass measurement. Or it could just be a kind of peaked galaxy that drops off quite rapidly compared to, and I don't know if there's like data at slightly low redshift that has looked into this.
I would expect that there are. I actually don't know that work. Maybe somebody else in the room does. Who wants to take a crack at that one? But I would imagine, yes, there are. I mean, the multiplex of the spectrograph is such that you know we have thousands of spectra, and any one object, the average object, is probably not helpful in the sense that it's maybe too compact, or not strong enough line emitter, or badly aligned to the slit, because we don't really control the direction of the slit very well. But you know, if 1 out of 20, you know, it makes for a good test, then you actually have plenty of examples. So I think it'd be about going through and sort of carefully curating a selection of things that you thought would actually be dynamically helpful. Now the other thing that is still, I think, more in front of us than behind us is the way that the data is usually taken is with the 1.5 arc second long slit. So if your object is too big, then you're going to the way that they do the background subtraction is sort of trying to subtract out the outer parts from the inner parts, and so you would have some self subtraction of the lines. So you want to be, for bigger galaxies, you would want to be avoiding that problem, either by using a longer slit or by doing a global background subtraction and not relying on global backgrounds, which, you know, I think will definitely be the way we're doing data reduction on near spec in 5 years. But it's just not the way we're doing it now, because
Can't you open a little slit along the way away from your target?
absolutely, yeah. So
This hasn't been done yet.
So we actually do open up those, we do open up spare slits, we just don't use them yet. So it's a software, my point is it's a software problem, not
That's good.
a hardware problem. So that's why I think all the people who would know enough to do that work are all just running flat out to keep up with the early data. But like in 5 years, surely we should be doing a global background subtraction. After all, you're in space. There's no background. Like, why are we spending all this time worrying about how to subtract the background when there isn't any, or very little.
Because like you said, this isn't like us fit into a groove cloud and heads inputs. So how
be good for us to try to make a cleaner plot of that. But, so first of all, you don't see that many classic red sequence galaxies at high redshift, because the universe just isn't old enough. So what you think of as a red sequence, you mostly are gonna turn more of a post-starburst type of SED, which is dominated by A stars, which is very distinctive, but just doesn't, it's just not quite the same. So I think that, so there's a portion of of the topic that you're looking at, which would be about how strong is the rest optical compared to the rest ultraviolet, and trying to get a feel for that. But then there's another piece, which is how blue is the rest UV continuum. And some of that worry would be about dust, but some of it's about stellar populations and stellar ages. And we do see examples in the survey of objects that are really blue, much bluer than zero color AV. So there's a story in there too, I think, about looking at the ultraviolet colors. We do have a small population of quiescent galaxies that are, that just are pretty weak in the ultraviolet and are not showing H alpha. So those are around as well.
Do you know what the state of the art is for modeling stars, massive young stars of low metallicity?
I don't know myself. There are various groups that are working really hard to do that sort of stuff, but I mean, there is uncertainties about, physical uncertainties about how those populations work.
Can you say something about morphologists? So you said that for some of them it is you might. So is it?
Yeah. Well, the thing I found really fun is that, when you're talking about redshift 5 or 6 or 7, okay, sure, a bunch of them are unimodal. You can then argue about how extended or what source of profiles or not, but there's a bunch of them that are not unimodal. So we see, close doublets. We see sort of sprays of like 5 or 6 points within an arc second. There's some of them that are kind of chain-like, but others that are not so chain-like. And I was, I guess going in, I was getting worried about being reasonably confident that we'd be able to do this, resolve things at redshift 4, 5, 6, but sort of thinking that, by the time you get up to redshift 10, they're all just going to be small and boring. Turns out not all. I mean, they're small, but they're not all boring. we do see binary, multi-lumped things at redshift of 8, 9, 10.
But is it like with the Hubble that about the redshift 2 it was also?
Sorry.
Is it like with Hubble when at redshift 2 about 2 it was like also they're regular JWST and Jesus? So is it like?
Yeah. So the worry basically that if you're just looking at the ultraviolet continuum that you're getting fooled.
Right.
I don't think it's as nearly as severe a problem with JWST. Even at redshift 9, you're starting to see over the Balmer jump. So I don't think it's as bad.
At redshifts greater than 10, what are the, is there evidence for dust? Has dust been able to form, like 10 to 15, say?
I don't know at redshift 10. We did have a paper claiming a detection at redshift 7 of the 2200 angstrom dust feature. So there is some evidence that dust is forming at redshift 7, or has formed by redshift 7.
But not by 10 or 12 or 15? The reason I'm asking is looking for top 3 stars, which we hope we can do something about, X-ray emission, gamma emission, but is dust then not an issue? Surely this has been modeled by the top.
No, the question is how do you decide you're detecting it? So I mean, by finding the 2200 angstrom feature, you have a relatively distinctive signature, and then the other thing you can often look for is the Balmer decrement, so the ratio of H beta to H alpha. And so that gets detected in some systems, but the H alpha leaves the spectrographic redshift 6.5. So once you get beyond redshift 7, you're looking at the higher Balmer lines, but the Balmer decrement's not as think there's any, I mean, I think it's clear that these galaxies are, the galaxies that we are seeing tend not to be very dusty. Whether there's a population of dustier ones is, probably yes. And we see some examples of like redshift 5, 6, 7. But by the time you're out to redshift 10, I think it's harder to see those examples of these so far.
Good. Thank you.
How about the luminosity function? Like, can we somehow compare the luminosity? Is the number of galaxies enough to like statistically see the effect of this, for example, in the luminosity function?
Effect of dust. How would you look?
No, well, like I was really interested to see how the usual luminosity function compares from redshift 7 to, like, for example, 12. And
Yeah, so people are definitely publishing papers trying to measure the luminosity function. In fact, there was a paper just a couple of days ago from Steve Finkelstein, as just one example of doing this. And a lot of that focus has been on whether or not the luminosity function of redshift greater than 10 or 12 is falling, is continuing to fall as it does from redshift sort of 5 to 9, or whether it's starting to flatten and have a longer tail. And I think these papers tend to find that it's starting to flatten, but I'm just nervous about it because if you have a rapidly dropping true population and a population of interlopers that is flatter, then you are naturally going to find a result that looks shallow. And so this is why I just get really nervous about false positives. And I'm not trying to throw Steve on. I'm not throwing shade on Steve. I think he's doing something very, very similar to what lots of groups are doing. I'm nervous that until we have stronger confirmations of the high redshift ones, I would not leap to think that the luminosity function is evolving slowly.
So this picture from Heinlein's
Yeah.
paper, the highest spectroscopic redshift is 13 or something.
13.2, yeah.
And then there's a whole bunch of these red guys.
Exactly.
And you think many of them could be false positives.
Well, and we say that in the paper.
I know, but what are the kinds of false positives?
Oh, it's
Expecting?
yeah. So it's generally you have seen a break in the spectrum. The question is that break strong enough? Lyman drop should be blue and complete drop, but a Balmer jump
Yeah.
would be kind of middlingly blue and then some drop, and we just see examples in the survey of galaxies that drop by a factor of 2 or 3 in flux across the Balmer jump. And yet we can see, because the data is deep enough, you can still see the UV continuum. And so if you're in that situation, then like nature can occasionally produce a rather large Balmer jump. And that's our worry, is that there's, so then your solution is exert even deeper into the UV.
But the problem is that you are interpreting it as a Lyman jump?
Yes, exactly.
Okay,
Occasion
so
between
you
Lyman
think
jump-
it's a Lyman jump, but it may just be a
Right,
Balmer jump.
because in the end what you've done is you've taken your SEDs and you fit them to a photo-Z code, and the photo-Z code is sort of trying to do the pattern matching of what low redshift templates look like, what high redshift templates look like, and producing some chi-squared versus Z plot, and you try to tune those parameters as best you can, and you try to reject the low redshift ones as best you can. But if you're super conservative, then you never have anything. So you have to, you're always making a choice. And that's
Is that what we're seeing on the chi-square plot in the front, the double dip?
yeah,
Like, you have
absolutely.
that
Yeah, no, that's a great point. Yes, exactly right. So it's just this characteristic double dip, and in this case, the delta chi-squared is whatever you say, 50. That's pretty strong evidence. But if that delta chi-squared is 10, not incontrovertible. And people usually set the threshold around 4 or 5, which is not really super strong. So as we try to wrap up here, I thought I would just sort of direct our attention to this last item, which is the observation that I found most perplexing out of JADE so far. And look, it may not turn out, it may not pan out, but we'll see. So this was again GZ11, this very bright redshift of 10.6 galaxy, and when Roberto was looking at the spectrum, he noticed that it seemed like the helium-2 1640 line was slightly extended away from the main core of the galaxy by like a third of an arc second. And so we actually successfully proposed to get director discretionary integral field time on this object. And sure enough, when you look in the spectral channel that corresponds to helium-2 1640, there's this cloud, which is off-center by, I can't remember, something like 0.4 arc seconds away from the galaxy. So it's not in the galaxy. And yet this cloud shows no general continuum and has no detected Balmer lines. But admittedly, H alpha and H beta are both out of band, so you're looking at a pretty weak Balmer line. It does not have Lyman alpha, but of course you can always explain away Lyman alpha at high redshift with the Gunn-Peterson trough, so maybe that's not surprising. Although GNZ11 shows Lyman alpha, so there's some window there. But yeah, so you have this cloud that shows no metal lines, it's just glowing in helium 1640, and usually that requires a very hard ionization source. And when you work out what the energetics are, you have to be driving a lot of energy into this cloud. So it is not, even though we do think that GNZ11 may have an AGN, it is not that this AGN is lighting up and fluorescing and shooting out and hitting that other cloud. It would have to be, the off-axis flux would have to be, or the on-axis flux would have to be suppressed by a factor of 100 relative to the cloud, the flux that have to be heading this cloud. So we don't think that it's being fluoresced by 11. So you're looking for some internal source. The internal power source, if you work out the energetics, if you convert the energetics to an Eddington mass, Eddington luminosity convert to mass, it has to be a 10 to the 6 solar mass level of energy going into this thing. So that got our attention. Now we'll see if the cloud bears out. We've seen it twice, so kind of should be probably real. But we actually have some more observations coming up on it, so hopefully it will bear out again in the third go round.
This was the guy you're looking at.
Yeah, that's right.
Why would you think it's not real?
Yeah. No, I mean, yeah.
Why would you even worry? That's what I'm asking.
Yeah. No, it's not so bad. It's not so bad. Like, so I mean, the real problem here is like, so what could this be? So this version that we got interested in about, could it be a cluster of POP3 stars, which would produce very high, very blue radiation that might, if it's a pristine cloud, then you would not expect metal lines. If it's blasting away with some incredibly blue spectrum, then you could explain the helium-2 ionization. You would still get hydrogen, but as I say, the hydrogen, maybe we just couldn't detect the weaker lines. So of course we're hoping we can get back with longer spectrum to look for it's H delta in this case, or maybe it's H gamma. It's a hard one. But another possibility is it might be some cloud that's having a direct collapse to a black hole. That'd be another way to get a lot of radiation out of something. So this seems like the thing we found that really doesn't fit into the usual stellar pop galaxy formation sort of story. So we'll see if this bears out, and if the data comes in. But I found it really interesting. So
It sounds like a Vorbeer.
Yeah.
Like Hannes Vorbeer.
Yeah.
Where there was a bright quasar pointing that way 1,000 years ago, but not now.
Could be.
What are the other bright sources in the northeast? There's one in F277 and one in Lyman alpha.
So do you mean in the upper left corner?
Upper left corner, yeah.
That's a neighboring galaxy.
Okay.
That's at like redshift 2, so not associated.
And what about the Lyman alpha cloud? Did you see anything in the contours? Also.
Yeah, we think that there's a Lyman alpha cloud coming off of GNZ11.
Okay. Well, no, I mean there's like another one, right? Or is that? But that's associated with GNZ11, like the one that's kind of offset.
Yeah, we think those are offset, and unfortunately, this data. One of the reasons that this data's being taken again is that the telescopes had a mispointing when it was taking the data. So we intended the GNZ11 to be centered in the IFU, but it turned out it only clipped onto the edge of the IFU. So this is really what we get. What we get for real information.
What's the reference X-ray for redshift 10?
Sorry, what's the
Like reference X-ray, because if it's a like something like gas around,
sure GNZ 11 has been.
I thought there was only an upper
I mean,
limit.
well, this is in the Chandra Deep Field North, so there's like 4 megaseconds of data.
Maybe
but I
Bill
don't
or Christine.
think it has.
Do you know about if there's a protection of GMT 11? I thought it was an upper limit.
No, I don't know.
That's not
I don't know the JWST.
Just a simple question. If this cloud only shows up in helium 2, so essentially in a line with no continuum, how do you confirm this cloud itself's redshift? Could it be somewhere?
Yeah, so that's an example of the uncertainty. So we think the line is there, but if somehow it was, if it's some other line from some other, the line identification would be way, but we only have a single line right now. So indeed, that's one of the outs is that we're incorrect in interpreting the thing that's redshift. It does happen to match the redshift of helium 1640 and the redshift of GNZ 11, so it's like, it's not that any line would have worked, any wavelength would have worked, still.
Has anyone done the kind of timescale argument of how, if it was an AGN in GNZ 11 that was blasting this thing with radiation, of how long ago it would have shut down?
Maybe somebody does know. I tend to think of these things as being an order of 1,000 years to get back to the.
Right.
I mean, it depends on the recombination time. Right?
Yeah.
Because
I feel that
time can be quite long. What if 03 in Hansfeld Borbeck, it's fairly long.
I would say that before.
Yeah, more than
years.
yeah.
So how much?
10 to 4 years.
So I would
That's
guess
really
that
that's
AGN,
the cloud, though.
an
It's a lot of
AGN
energy.
at this
I mean,
redshift will be
it's
quite varied.
it's not a weak thing, but a lot of energy. If
But
that lot
you don't think it's shining right now because you don't see it, but it could be obscure, right?
by a factor of 100, yeah.
Well,
It's hundreds of millions.
Miri, have you tried Miri? Off dust setting.
I think GNZ 11's been observed with Mary, but I don't know what wavelengths.
So Martin, factor of 100 obscuration, we're talking about in the UV, right?
Oh, yes.
Well, we're observing it all. No, it's not just in the UV. I mean, we observe out to, well, it's not, I mean, it's out to 4.5 microns in the basically, so it's out to 0.4 microns.
Yeah.
So it's not way out.
Right, but I think it should be possible to obscure an AGN, just the black hole environs by a factor of 100. I don't know.
Oh, yes.
It's doable.
In blue wavelengths, that's not a problem. But that's why I asked about Miri, because that then re-radiates at a few microns to the rest of them.
So, but if you, if the energetics is such that internally you need 10 to the 6 at Eddington, then externally you presumably would need more.
Yeah, you need a lot.
So, like if it's a factor of 100, because the externally then would it be completely out of line with what it had for mass projection? 10 to the 8 black hole, for example, that's such a thing. So that
Yeah.
you could-
And so, for example, you worry that the line widths that we see in the object might be incompatible with that, because we see,
If I
there's
remember-
lines in here that we interpret as coming from the AGN, and so we have to arrange for a situation where those lines would be narrow enough to, even if the AGN was, even if the black hole was performance.
If I remember right, the GNZ 11 black hole with the chunky error bar was inferred to be about 10 to the 6 or something, and accreting at slightly super Eddington.
That's right.
But it had a recent super Eddington burst. I don't know.
Yeah, that'd be hard. I mean, I think if you wanted to make it that luminous, you would have to say that the masses were really being underestimated by 2 orders of magnitude, which is to say the lines have to get 10 times wider. You have to make the lines 10 times narrower. Which, if you think we're not seeing the broad lines, then okay. But
How long after a drop in luminosity would it take for the lines to not be as broad? Genuine question, I have no idea.
Well,
the line lists are being set by the dynamics of the black hole, so I don't think that.
Right, okay,
I don't think
sorry,
that's going to get you out of it. But I think, yeah, the system will. I'm sure that stuff will respond quickly to the change in the accretion rates in terms of the strength of the lines. I just don't know that it affects the line list very quickly.
So has anyone actually looked into the X-ray image
I don't think I have. I mean, I don't think I've realized.
I think 10 to the 6, in terms of X-ray, predicted X-ray flux, I just remember numbers for rings, rings. It was 10 to the 4 black hole redshift can detect about flux 10 to minus 19, so 10 to the 6 is, and those results are private, 10 to the minus 17, which is nominally roughly a detection threshold for the channel.
Yeah, I think it's an interesting idea. I mean, I'm sure that GNZ11 has been looked, I'm sure that people have looked at the question of whether GNZ11 is detecting the X-ray. Because this object's been around for 10 plus years, and so is the X-ray data. I'm sure people have looked at that. And if they found a source 0.3 or 4.4 arc seconds away, I'm sure, my guess is they would have said something. But it's never hurt to look again. maybe one takes 3 photons more seriously. You have something else in there.
But it's challenging, right, in terms of angular resolution,
Yeah, it's hard. This one's hard.
0.3 arc second.
And I don't remember how close to the center of the Chandra field GNZ11 is. I don't think it's super close. So it might be that this is not, the data that's in hand is not.
And then the
Yes.
sensitivity will definitely be more than 2 months, definitely minus the general access.
Yeah, they got to do it. So. Well, cycle 3 just passed, but you should get your proposal ready for cycle 4, because it's a fantastic telescope.
That's a good last word.
Thank you.